optimization, and today we will continue talking about the quasi-Newton method. In the last class, we introduced to overcome the disadvantage of the Newton method. We propose this quasi-Newton method. Okay, so first we review. Generally speaking, for the unconstrained optimization problem, we can use this kind of line search. Actually, this is a little bit more general than what we have discussed before, because we use the decay, the gradient of f, instead of the direction. Okay, actually here, if we use the decay equals to the inverse of the Hansen matrix, it will become the pure Newton method, okay? Or if you choose the step size alpha equals to 1. And of course, instead of using the inverse of Hansen, because the computation of this decay here is very expensive, yeah? First you need to compute the second order derivative, and then you need to compute the inverse. If the metric is, the size of the metric is very large, it would be very difficult. So we propose the quasi-Newton method. The idea is we want to find a matrix BK here, which is a kind of approximation of the second order derivative. And on the other hand, the computation of this BK should not be very expensive. What does it mean? It means to update the BK should be simple. Because in the Newton method, in each iteration, okay, you need to compute the inverse of Hansen again, okay? I mean, you need to compute a new Hansen and compute the inverse. But our idea for update the quasi-Newton matrix is that we want to get the next BK plus 1 just from BK with very small modifications or very cheap computations, but it can preserve the good properties like the symmetric or the positive definite, okay? And one of the best or one of the most practical choice is the BFGS, okay? And the approximation of the Newton, which BK plus 1 is updated by this formula. So it's a kind of rank 2 modification. You have the BK and you have 2 rank 1 matrix. So generally speaking, the computation in this formula is cheaper, much cheaper than the Newton method, okay? And okay, today we will discuss about the convergence result about this quasi-Newton method with BFGS updating formula. We will mainly discuss the global convergence, and later we will mention a little bit about the local convergence, which is superlinear under some proper assumptions, which is also one of the biggest advantage of the quasi-Newton method. Okay, so before discussing the convergence, we need several things. First is we review the Wolf condition. Okay, so the step size in the length search scheme, alpha k, satisfies the Wolf condition if the following two inequality holds. Okay, the first is sufficient descendant condition, which you can also call it the Amijo condition. Yeah, if step size only satisfies the first one, we say it satisfies the Amijo condition, and the first one. And the second one is called the curvature condition, okay? Curvature condition. And the C1, C2 are some constant between 0 and 1. Actually, in the quasi-Newton method, for example, in the BFGS, we mainly consider about the Wolf condition instead of the Amijo condition. The reason is if you only use the first condition here, you cannot guarantee the BK plus 1 is positive. Okay, we cannot guarantee the BK is positive definite. If it is not positive definite, we cannot guarantee the direction here. This direction, okay, is a descent direction. So in this case, we prefer the Wolf condition in the quasi-Newton method. Okay, And another important tool to prove the convergence for the quasi-Newton method is this theorem, okay? It says if we consider a line search method and the direction is a descending direction and the step size satisfies the Wolf condition, okay? So descent direction plus Wolf. And we suppose f is bounded below. Of course, this is trivial. Yeah, if your function is not bounded below, maybe your optimization problem is not well defined. And f is also continuous differentiable, okay? In an open set N, which contains a level set, this level set, and we assume that the gradient is Lipschitz continuous on this open set N with constant L. Then we can, sorry, there should be an infinity here, okay? This summation is less than infinity, or we say this term is summable. The idea to prove the convergence by this theorem is that since this term is summable, okay, we can know that this term approaches 0 as k approaching infinity, okay? And if we can prove that this cosine square theta k is bounded away from 0, then we can know the gradient, the norm of the gradient will approach 0. Okay, so this is the main idea of how do we implement this theorem to prove the convergence, not only for quasi-Newton method. For example, this can also be used for the conjugate gradient method, which we will introduce in the next class. Okay, so let's say how do we prove this? Actually, it's not very difficult. So by the definition of the line search and the curvature condition, we have this, okay? So this just came from the second inequality of the Wolf condition. And then we use the, and then we use, not then, and we also use the Lipschitz continuity of the gradient, okay? We can get this condition very easily. Then we combine these two inequalities together, okay? So we can get a lower bound about the step size, okay? Alpha is greater than these terms. And then we put this term together with the sufficient descent condition, which is the first inequality in the Wolf condition, okay? Then we got this inequality, okay? Actually, it's the upper bound. It's a bound of the increment of the function value. Okay, from this inequality, we can define the angle theta k between the direction, the searching direction, and the negative gradient. Okay, the minus gradient as this. Okay, this is the classical definition of the cosine of some angle. And then we can rewrite this inequality, especially here, by the definition of cosine theta k. So the last inequality became like this, okay? And the c is just equal to c1 times 1 minus 2 over L. And we know this this term is positive, yeah, because c1 and c2 is between 0 and 1. Okay, so next we summing these expressions over all the indians, over all k from 0, over all j, okay, over all j from 0 to k. Then we get this one, okay, we get this one fxk is less than fx0 minus the summation of this term. Remember that in the theorem, we assume f is lower bounded, okay? So we can know this term, okay, the fx0 minus fxk plus 1 will be bounded. Okay, then we take the limit. So this term we know it's summable. Okay, this term we know it's summable. So we prove the first theorem. Okay, prove the third theorem. Okay. Actually, this similar result, actually, this inequality also holds for some other line search conditions like ghosting conditions or even strong Wolf condition. Of course, if if it holds for Wolf, it also holds for the strong Wolf condition, and it's called the Zutandijk condition. Actually, this as I mentioned, this can be used for the analysis of the convergence of many algorithms. Okay, and as I mentioned, if f is not bounded below, then the problem will not be well defined. Okay. And the Lipschitz continuity of the gradient of the objective function is not very strong. In many local convergence theorems, you can find some assumptions which can derive this condition. Let's summarize a little bit how will we use this to get the convergence. Okay. So the Zutandijk condition implies this approaches 0, and sorry. Okay, so in the line search, okay, in the line search scheme, if the decay ensure, if we choose some decay that the angle theta k is bounded away from 0, which means it can be not orthogonal to the negative gradient, okay? It cannot be orthogonal to the negative gradient. Then the cosine theta k or cosine square theta k will greater than some delta, which is strictly greater than 0, okay? If we have the upper bound of this, holy sh, I'm sorry. I clicked the wrong button. Okay. So if we can choose some decay such that the angle can be bounded away from 0, then we can find, we can derive that this cosine is upper bound, okay? And then we can, okay. Holy sh, now I know. Okay, so it follows immediately that the limit of the norm of the gradient will equal 0, okay? And then we can see that the norm of the gradient will converge 0 if the direction are never too close to the orthogonality with the gradient, okay? So this is the general idea. How do we use the Zutandijk condition to prove the global convergence of some algorithms? The key point is you need to prove the direction is not orthogonal to the negative gradient, or the angle is bounded away from 90 degrees. This is the main idea which we will talk about today about the BFGS, okay? And we give some examples of the implement of the Zutandijk condition. The first is the steepest descent direction. Okay, if we just choose decay as the negative gradient, then we can get immediately the cosine theta k is 1, and then its upper bound it has a lower bound 1. Okay, and then it converges. Okay. Okay, and for Newton, for example, the next example is for the Newton method. Okay, the direction, the Newton direction is like this. The decay is minus the inverse of Hansen times the gradient. Okay, if we assume that the inverse of Hansen is positive definite and with a uniformly bounded condition number, then we can also prove the cosine theta k for the Newton method also has a lower bound. Okay, let's check it very quickly. So first, by the definition of condition number, we know the kappa of the inverse Hansen equals to the maximum eigenvalue over the minimum of the eigenvalue. Okay, and the minimum of the eigenvalue. The minimum eigenvalue of the inverse matrix is equals to the maximum eigenvalue of the Hansen matrix. Okay, so because we assume that the condition number is uniformly upper bound. Okay, upper bound. So we know the norm of the Hansen times the norm of the inverse of Hansen is less than m, and then by the Rayleigh quotient and the spectral norm, we can see that the cosine theta k, the first is just by the definition, and then we use the Rayleigh quotient here and the spectral norm inequality. So we get this is greater than, this is the minimum of the minimum eigenvalue of the inverse. Okay, and then it equals to the minimum of the inverse over the maximum of the inverse. Okay, and we can put this term here. Okay, we can put this term here. Just becomes minimum eigenvalue with inverse. Okay, and this equals to the this is the master eigenvalue of the inverse, and this is the inverse of the minimum of the eigenvalue of the inverse, and it equals to the maximum of the eigenvalue of the Hansen, and which this term is this term in the denominator is less than m, so the whole term is greater than 1 over m. Okay, so you see here you have a lower bound which is strictly greater than 0 of the cosine theta k, and then you use the Zutendijk condition. You can prove that the Newton method with the Wolf condition and uniformly condition number, then it will converge globally. Okay, and okay, next we will see. Okay. Before we go to the global convergence, we already recall what is BFGS, and recall the Wolf condition, and also this theorem 1, which is called the Zutendijk condition. How do we implement it to prove the convergence? Next, we need some preliminary result from mathematics to prove our result. Okay, the first is the trace of the metric. The trace of n times n metric is defined by this. It's the summation of the element in the diagonal element. Okay, and the linearity is the first property is linearity. The trace of a plus c times b is the trace of a plus c times the trace of b, and another is a cycle invariance of the products. The trace of a times b times c equals to b times c times a equals to the trace of c times b a equals b, but usually it will not equals to the trace of c times b times a. Okay, you can just do the cyclic transformation, but you cannot exchange a or a with b. And another is another is about the eigenvalues. Okay, the trace of the matrix A is equals to summation of the eigenvalues. Okay, and another is about the determinant of the matrix. Okay, the first is the determinant of matrix A is the product of all the eigenvalues, and the determinant of A times B equals to the product of the determinant of both A and B, and this is quite important in our analysis, because we know that the BFGS is a kind of rank 2 modification. So about the determinant of the rank 2 modification, we also have the result. Okay, this result about its determinant, which means the determinant of this rank 2 modification equals to the difference of these two products. Okay, of these two products, and we will use we will use this in the analysis of convergence. Okay, then we go to the convergence, global convergence of the BFGS. Actually, even if the BFGS is very practical and robust in the practical computation of for many real problems, even for many nonlinear, non-convex optimization of functions. But unfortunately, generally speaking, we can not every non-convex function will converge, or we can see the BFGS cannot converge for minimizing any nonlinear, non-convex function. There is counterexamples about it. So about the global convergence, we have some proper assumptions. Okay, so first we introduce assumption. First, we need to assume that f is twice continuous differentiable, okay, twice continuous differentiable. So, which means the gradient is also continuous differentiable and it is also Lipschitz continuous, okay. And second is the level set, okay, this level set is convex. And there is a positive constant m and capital M such that for any z belongs to Rn, that z transpose Gx, z, actually this G is the Hansen matrix, okay, is greater than m times the norm of z and less than the capital M times f. This means the eigenvalues of the eigenvalue of the Hansen has upper bound and a lower bound, okay, has a positive upper bound and a positive lower bound. We actually, this lower bound means the f is not only convex but also strongly convex, okay, also strongly convex. And here we see the part 2 of the assumption implies a G, which Hansen is a positive definite, okay, on this level set. And f has a unique minimizer on this level set. Okay. Okay, next. Before we go to the analysis, let's recall some preliminary result. First, we recall the definition of yk and sk. Okay, yk is the difference of the gradient, and sk is the difference of the iterates. And then we consider the first order Taylor expansion. Here, actually, it's not approximate, it's approximation, it's the equality, okay? The gradient of the f at point xk equals the gradient of f plus this integral from 0 to 1 about the Hansen along the direction of sk, okay? Then we can see that the yk just equals to the difference of the gradient. So it's equals to this integral times sk, okay? And we define this integral as a g bar k. Actually, this is called the averaging of the Hansen. Averaging of the Hansen along the direction of sk. Okay, immediately we have that the yk transpose xk equals to sk transpose g bar xk sk. Okay, remember this is the first preliminary. It's true. Computation is trivial, but remember it in mind. And then the second one is for a fixed z belongs to Rn. We define this invariant function phi t, which is a z transpose g xk plus t sk z. Okay, so since this g, the Hansen satisfies this inequality for all d belongs to Rn, and x is this capital L, which is a level sub-level set, is convex. Okay, then we know that this phi t is greater than m times the norm of d and smaller than capital M times z square. for any t belongs to 0 and 1. This because the x, we already assume FL is convex, okay? Then x plus t sk belongs to L for all 0 belongs to for all t from 0 to 1. Okay, this just because the convexity of the sublevel set. Okay, then from this inequality, we take the integral on both on three sides of this inequality, and then we have this inequality about the integral, and this is a constant, and on the most right side is also a constant. So we have this is just m times the norm z square, and this is z transpose. This is the averaging of the Hansen day, and this is exactly equals to z transpose g bar gk bar z is less than this. Okay, so this is a second preliminary result what we get here. Okay, it's actually in the assumption we only have this inequality about the Hansen, but here we can also derive the similar inequality about the averaging of the Hansen, which is gk bar. Okay, so combine these two inequalities. Let's recall a little bit what we get. First is the yk transpose sk equals to sk transpose the averaging of the Hansen sk. And the second and the second is about the inequality of the, actually it's the eigenvalue of the averaging Hansen is upper bound by a small l and lower bound by the capital L. So we put these two together, we can get this yk transpose xk over sk transpose xk is just equal to this. The first inequality is because the first preliminary result, and the inequality is just because the averaging Hansen matrix is bounded by small l. Okay, and since this averaging Hansen gk bar is positive definite, okay, so the square root is well defined, and we define the zk is equals to the gk the square root of the gk bar times sk. Then we can rewrite this yk transpose yk over yk transpose sk equal to, so the first equality because of the first preliminary result, and this one, and the second inequality just because of the definition of the zk here, and then we use that the gk bar is bounded by the capital M. Okay, we can write these two preliminary result here. We use the first one is that yk transpose sk is equals to sk transpose gk bar sk. So this is the first one, and the second one is that m times the norm of this square is less than the z transpose gk bar z is less than m the norm of z for any z belongs to the whole space. Okay, so these two preliminary result is used in this slide, both in the first relation and the second relation. Okay, so up to now we have this result, and this result we can go to analysis of the BFGIs. Okay, sorry about the typo here. Okay, sorry. The convergence about the BFGIs is that for any B0 is the initial approximation of the Hansen. Okay, for any B0 is a symmetric positive definite, and the x0 is a starting point, and for which assumption 1 is satisfied. Okay, then the sequence generated by BFGS converges to a minimizer x star of f. Okay, to prove this result, the idea of the proof is not very complicated, but there are some notations which looks a little bit complicated, but it's just for simplify the convergence. Okay, first we define the mk equals to yk sk over sk sk. Okay, and the capital mk equals to yk transpose yk over yk transpose sk. Okay, according to the preliminary result, we know the mk is greater than m and the capital mk is less than m. We can go a little bit, okay? So actually we just define this term is a small mk and this term is a capital mk, okay? So this small mk is greater than m and this capital mk is less than m. So this is what we conclude here, okay? It's just the some previous result. Okay, next we begin from the update formula of the BFGS. So this is the rank 2 modification of BFGS, okay? So first we consider about the trace of the BK plus 1, okay? So we compute the trace of BK plus 1, it's equals to the trace of this rank 2 modification by the definition. And by recall, the first property of the trace is the linearity. The trace is a linear functional, okay? So it can equals to the trace of BK minus this, because this is scalar, yeah? This is scalar. So this scalar times the trace of this matrix and this scalar times the matrix. So first is because of the linearity of the convex of the trace. And to get the third equality, we just use the cycle invariance of the products of the chains. Okay, so actually you can, because you only have two matrices here, so you use the cycle invariance. So you can just exchange the position of these two matrices. So you get this one, but this is just a scalar, okay, and it is similar to this. So you get this result. So the trace of k plus 1, the trace of the bk plus 1 just equal to the trace of bk minus these two scalars. Just because of the property of the trace of a matrix. And then, holy shit. Okay, next we compute the determinant of the bk plus 1, okay? And actually the determinant of bk plus 1 just equal to this. I didn't put the computation here, but recall when we in the preliminaries of this slide, we discussed about the property of the trace and the property of determinant of matrix. One of the conclusion about the determinant of matrix is about the rank 2 modification. Okay, rank 2 modification. You use that conclusion here directly. You can get the determinant of bk plus 1 equals to the determinant of bk times this scalar. Okay, and then we define the angle between sk and bk sk is this, just by the definition of the cosine. Okay, and the qk is this term, is this scalar. Okay, and then we can say this term. Maybe you are confused why we are discussing about this term. Later you will understand maybe several minutes later. So this term can be rewrite as this. Okay, you have one term in the numerator and one term in the denominator. And then this, so 1 is qk, okay? So this term is qk, and this term is the cosine square theta k, okay? And we can also rewrite this term as the term in the denominator on the expression of the determinant here. The determinant of the bk plus 1 equals determinant of bk times, you have one term here and one term here, and this term is mk, and this term is the 1 over qk. So the determinant of the bk plus 1 can be written as determinant of bk times mk over qk. Okay, so please remember these two conclusions here. Okay, later we define a function per se b equals to the trace minus the log of determinant, or the log of determinant of bk. And this, it is easy to check. This function is greater than 0. Okay, this function is greater than 0. And no, it's not easy to we need to check here. This function is greater than 0. Okay. Let me see. So we consider this per se bk plus 1 equals to, by the definition, is equals to the trace of bk plus 1 minus the log determinant of bk plus 1. Okay, by the computation before, we can just substitute the trace of bk plus 1 by these three terms. Okay, and also by the substitute the determinant of bk plus 1 by this term. Okay, just some conclusion we get in the last slide. And then we can use the property of the log function. Then we can get this equality. Okay, and we rewrite this inequality. We have this. Okay, we have this. This per se bk plus 1 just equal to per se bk, because you have the trace of bk and you have the log of determinant of the bk. So you have the per se bk and the mk minus the log mk minus 1. And you have this term related to the qk and cosine square theta k, and plus the log cosine square theta k. Okay, remember, we discussed a little bit about this function ht, which is equals to 1 minus t plus the log t. This is non-positive for all t is greater than 0. Just by some computation, you can computation the first derivative and secondary derivative, and you can find it's a concave function, and the global maximum is 0 at the point t equals 1. Okay, so this is positive, non-positive for all t greater than 0. And then we combine with the previous conclusion. The previous conclusion is we rewrite the per se bk plus 1 equal to this term. Okay, and this is and this is because this per se function is greater than 0. Okay. Oh, sorry about that. Let's mention a little bit. This is greater than 0. You can use the definition of the trace and the definition of the determinant, because the trace is a summation of the eigenvalue, and the determinant is the product of the eigenvalue. You can prove it directly by the definition. Okay, so this per se is greater than 0. So per se bk plus 1 is greater than 0. So we have this. Per se bk plus 1 is equal 0, and this is less than or equals to per se bk plus this term and plus this. Actually, what term is missing? This term is missing. Okay, this term is missing because this function ht is greater than is non-positive for all t is greater than 0. Okay. Actually, I think there are some typos here. Okay. There are some typos here. Here should be the qk over cosine square theta k. Okay, cosine square theta k. Sorry, there is a typo here. But anyway, we want to say this term is non-positive. Okay, non-positive for all positive t. Okay, for all positive t. Actually, the t is qk over the cosine square theta k, which is positive. Okay, so the term in this bracket is non-positive. So this is why we get the second inequality here. So this per se bk plus 1 is less than per se bk plus this term, okay, and plus the log cosine square theta k. And actually, we can, m, the capital M minus log m minus 1 is greater than m, the small m minus log small m minus 1 is greater than 0. Okay, so this is how we get the last inequality. Okay, and we also use this argument several times until the k equal to 0. Okay, so that's why you have the k plus 1 here, you have a summation here. Okay, you use the similar argument from k to 0. Okay, k to 0. So we get, so what we get? We get this per se b0 plus this term, this is some constant, and this summation, not the constant, this constant times k plus 1, and this summation is greater than 0. Okay? The idea is, actually we want to prove that the cosine theta k is lower bounded. Okay? It has a lower bound which is greater than 0. Then we can use the Zutendijk condition to prove the global convergence. Okay? So to prove the cosine theta k has a lower bound, we prove it by contradiction. So we prove there is some cosine theta k, there is some subsequence. Okay? Subsequence that cosine theta k can approach 0. Okay, so there we assume that there exists a k1 greater than 0. Okay, for all I greater than k1, we have the log of the cosine square theta k is less than 2 minus 2c, okay? Because this could be approaches 0, so this can be approaches negative infinity, so you can also has upper bound of this log function, okay? So we combine this conclusion with the previous conclusion together. So the previous conclusion is the per se b0 plus c times k plus 1 and plus this summation is greater than 0, okay? And we divided this summation to two parts. The first is from 0 to k1, and another is from k1 plus 1 to k, okay? So, and for the second term, this is less than 2 minus c, okay? 2 minus c, and this one, and this one is somehow constant, okay? And actually, for k large enough, because you see here it's just a c, and here you have minus 2c. So this term cannot be greater 0 anymore for large enough case. Sorry about the, I have checked my slide, but I didn't expect this will happen. So, so we conclude, what we conclude for large enough k, this term can denominate can denominate the whole terms, okay? So these terms cannot be greater than 0 anymore for large k enough. So what we assume is not correct. This cosine theta k cannot approach 0, okay? So there exists a subsequence with ik such that the cosine theta ik is greater than delta, which is strictly positive, okay? So here, and remember the cosine theta k. The definition of cosine is here, is the angle between sk and bk sk. And it's also the angle of the quasi-Newton direction and the negative direction, okay? Here, we use the definition of xk, okay? xk equals to xk plus, sk equals to xk plus 1 minus xk, and just equals to this. This is the best definition of quasi-Newton iteration. So you just substitute sk and by this, okay? And the bk sk is by the minus alpha times the gradient. You can have this. So from this expression, we can say the theta k is also the angle between this direction and the negative negative gradient. So we know the cosine theta k has a lower bound, which is strictly positive. So which means the cosine of the angle of the direction of the quasi-Newton and the gradient is bounded away from 90 degree. Okay. Here, the explanation here, just want to say this theta is also the angle between the quasi-Newton direction and the negative gradient. Okay. So we can use the Rutendic result. We know the limit inf of the gradient approaches 0. Okay, the limit, because here you only have a subsequence. The result is about the subsequence here. And actually, even if we just have the limit sup here, limit inf here, we can also get the whole convergence of the convergence of the whole sequence, because of your function is strongly convex. Okay, because f is strongly convex, and we assume that x star is the global minimizer of the f. So we have this estimation about the gradient, the normal of the gradient. Okay, and then we can just use the substitute xk by the xik, the subsequence here. Okay. And then we take the limit. I don't know whether it is, and then we take the limit here, and then we take the limit here. We can know that the xik approaches the x star, okay? The subsequence of xik approaches the minimizer, okay? And then since the Wolff condition is satisfied, we know the algorithm is a descent algorithm, so the function value is decreased. So we can, and since the function is lower bounded, we can assume that fxk approaches the f bar, and because the unique minimizer, so this f bar is equals to the fx star, and we can also use the quadratic growth of the strongly convex. We have mentioned before. The fxk minus fx star is upper bounded by this quadratic term. So we take the limit on both sides. We take the limit sup on both sides. We can have that the xk approaches x star. And since the Hansen is continuous, and so the gradient is also continuous. So we can see that xk approaches x star. We can conclude that the gradient also converges to the solution. So this is the global convergence about the BFGS under the Wolff condition, okay, under the Wolff line search, and some and the assumption 1 about the f about the objective function. Okay, about the local convergence. We know that the quasi-Newton method, like BFGS and DFP, it converges. If it converges superlinearly. But actually, the analysis is quite complicated with a lot of techniques. So we just give a very general result about the local convergence. Okay, it's like this. If we assume f is twice continuous differentiable and x is generated by some quasi-Newton method, any quasi-Newton here, in this is general conclusion, it may be BFGS or DFP or any Boyden, any matrix from the Boyden class. Okay. We assume that xk converges x star, and such that at the x star the gradient is equal 0 and the Hansen is positive definite. Then the xk converges superlinearly if and only if this holds. This means the approximation of the Hansen bk will approach the Hansen very well as k approaches infinity along the direction of the decay, along the quasi-Newton direction. Okay? But the problem is, how do you establish this kind of approximation? Or how do you conclude, for example, in BFGS, your BK can approach the real Hansen very well when k approaches 0. This is quite complicated. Okay, so we just introduce this very general local convergence result about all kinds of quasi-Newton method. As long as your BK can approach or can estimate the Hansen very well, but just along the direction of quasi-Newton method. Okay, if you have this very good estimation of the BK, you will have the superlinear convergence result. Okay, and the reference is about 2 books. One is from Bertsekas, Nonlinear Programming, and another is from the Numerical Optimization. And actually, in the main convergence result about the global convergence, you can find in the 2nd book. And you can also find the detail about the local convergence of the BFGS, but it's very complicated. It's not very difficult, but it's complicated. Okay, so in next class, we will go to the conjugate gradient method. Okay, that's all.